Welcome! Today we're going to peel back the cover on something that keeps our entire modern world running, electrical insulation. I want you to think of it as an invisible shield. And today we're going to learn how to spot the cracks in that shield before they turn into a total catastrophe.
Okay, so to really get this, let's start with a really simple but powerful analogy. Think about the plumbing in your house. Now, what in the world could that have to do with the wiring that's hidden in your walls? Well, turns out, a lot more than you'd think.
So check this out. In a water system, right, you've got pressure from a pump that drives the flow of water. And what contains it? The pipe. If that pipe leaks, you've got a mess. Well, in an electrical system, voltage is the pressure, current is the flow, and, this is the key, the insulation is the pipe. Its one and only job is to keep that powerful current exactly where it's supposed to be. Because an electrical leak, well, that's not just a mess. It's a fire hazard, a safety risk, a complete system shutdown.
So, when we talk about good insulation, what we're really talking about is high resistance. It's all about how strong that invisible shield is, how hard it's fighting to stop that electricity from leaking out. The higher the resistance, you guessed it, the stronger and safer the shield.
But, and here's the catch, no shield is going to last forever. I mean, from the second it's put into service, that insulation is under a constant, silent attack from all kinds of invisible enemies, and they're all working to bring that shield down.
And just look at this list. We're talking mechanical nicks and scratches, the constant hum of vibration, crazy temperature swings, corrosive air in a factory, dirt, oil, and, of course, the big one, moisture. All of these things are just relentlessly chewing away at that protective layer, creating these microscopic pinholes and cracks that you would never, ever see with your naked eye.
But here's the good news. It's not like it just blows up out of nowhere. It's usually a slow, silent decay. And that gradual decline, well, it gives off really clear warning signs that failure is coming. But you only see those signs if you know how to look for them.
And this is exactly why we have to look. You see, those tiny cracks become escape routes for the current. And we're talking about a current that can be as small as 1/1,000,000th of an amp. It's a tiny, tiny trickle, yeah? But it's more than enough to turn that protective shield into a direct hazard. You're risking equipment damage, super expensive downtime, and, serious danger to anyone working nearby.
So the big question is, how do we diagnose a problem we can't even see? Well, that's where insulation resistance testing comes in. It's basically our way of giving that invisible shield a complete and thorough medical checkup.
And to do this, we use a very special tool, often just called a Megger, or an insulation tester. Think of it like a high-tech diagnostic scanner for your whole electrical system. It applies a very safe, specific DC voltage, and then it precisely measures the insulation's resistance in millions of ohms, or what we call megaohms.
Now here's where it gets really interesting. What is that tester actually measuring? Because it's not as simple as it looks. The total current that it's detecting is really made up of 3 totally different parts, and understanding these 3 is the real secret to getting an accurate diagnosis.
Okay, first up, there's this quick surge of current called the capacitance charging current. It's just like when you turn on a garden hose. There's that initial rush of water that has to fill the empty hose first, right? This current does the same thing. It just fills the electrical capacity of the component. And then, poof, it's gone in seconds. Totally normal, totally expected.
Next up, we've got the absorption current. This is the current that the insulation material itself actually soaks up, kind of like a dry sponge absorbing water. This one also starts high and then it tapers off as the material gets saturated, but it takes a little bit longer, usually a few minutes. Again, this is totally normal for good, healthy insulation.
And finally, we get to the one that really matters, the leakage current. You see, while those first 2 currents were temporary and normal, this one is different. This is the small, steady current that is actually escaping, leaking through the cracks and over any contamination. This is the true leak in the pipe. This is the villain of our story, and measuring it is the key to finding out if you've got a problem.
Okay, so the tester spits out a number for us, a reading in megaohms. But what does that number actually mean? I mean, how do we turn that piece of data into an actual decision? Let's decode these results.
So we really have 2 main ways we can run this test. A spot reading test is kind of like taking a quick photo, a snapshot. It's one reading at one moment in time. It's a useful data point, sure, but it doesn't give you the whole story. Now, a time resistance test, that's more like filming a short video. By taking readings over, say, a minute, we get to see how the insulation behaves under pressure. This is way more conclusive because in healthy insulation, that absorption current we talked about drops off, which makes the resistance climb up. And a video always tells you more than a single photo, right?
And here's a really powerful pro tip for you. If you simply divide the 60-second reading by the 30-second reading, you get what's called the dielectric absorption ratio. And this simple number, this ratio, it tells a whole story. If your ratio is nice and high, say above 1.4, it means your resistance is climbing just like it should. Your insulation is in good shape. But if that ratio is low, that's a huge red flag that moisture or dirt is creating a leak. It's a quick, and believe me, an incredibly effective health check.
All right, now for what might be the most crucial point of all. A single test is just one data point. It's useful, yeah, but the real game-changing insight comes from tracking the trend. By testing periodically and recording all the results, you can literally see the future. That trend line, that is what gives you a clear, undeniable warning of problems that are coming down the road.
And this just perfectly illustrates the power of that trend. Look, in January, everything's great, 20 megaohms. By July, though, that reading has dropped all the way to 5. That right there is our signal to investigate before it becomes a crisis. By October, we're in the danger zone, and we need to take immediate action. When you plot these points on a graph, you see this clear downward slope. It allows you to predict and prevent a catastrophic failure before it even has a chance to happen.
And this brings us to the ultimate goal of all this testing, right? It's to get out of that costly, chaotic world of reacting to failures and fires and move into the much smarter, safer world of proactive, preventative maintenance.
And you know what? Building that program is a pretty straightforward 5-step process. First, you figure out what your most critical equipment is. Then, you test everything to get a baseline, your starting point. You diligently record every single test result. You set up a regular schedule. And finally, and this is the most important part, you analyze those trends. This is how you catch problems early. This is how you plan for repairs on your schedule, saving huge amounts of time, money, and of course, making sure everyone is safe.
In the end, this whole process is really just a simple health checkup for that invisible shield that powers our world. It's the only thing standing between a completely normal day and a very, very bad one, which really just leaves us with one final thought. When was the last time your shield got its checkup?